So with polynomial functions were always continuous. Rational functions, on the other hand, may have discontinuities, and they may have different types of discontinuities. So let's start by looking at this function. Let's find its domain, and to do that we set the denominator equal to 0, and solving that by factoring. X squared can be broken up as x and x. And then negative 3 could be plus 1 minus 3. We can check that by FOILing. And so this would mean x plus 1 equals 0, or x minus 3 equals 0, which means that we have x equals negative 1 or positive 3 that need to be excluded from the domain because they will make the denominator 0. So our domain will be negative infinity to negative 1 union negative 1 to 3 union 3 to infinity. Now let's check what's happening with the graph at these two breaks in the domain. So we have a break at x equals negative 1 and a break at x equals 3. So graphically speaking, what's going on? If we look at x equals negative 1, we have a line that we approach, and at x equals 3 we have a line that we approach. We call these vertical asymptotes. So let's look at this function. Here, the denominator, you'll notice, is the same as before. So if we set the denominator equal to 0, we end up solving the same equation. No need to solve it again. The domain is going to be the same. Negative infinity to negative 1 union negative 1 to 3 union 3 to infinity. So what we're going to do is we'll now look to see how these breaks in the domain correspond to features in our graph. So if we graph our function in Desmos, it can help us out. So what I'm going to do is I'm going to click on the graph, and whenever I click on the graph, it'll show me the ordered pair that corresponds to that place on the graph. So right now, at x equals negative 1, it doesn't appear like there's anything of note. Notice with x equals 3, we still have that vertical asymptote that we saw in the previous example. So let's see what happens whenever we click on the graph and we look around and at x equals negative 1. So if you notice at x equals negative 1, we have a hole on our graph. I would encourage you to plot this in Desmos and see for yourself what's going on with negative 1. But we do have a hole. Our function cannot be negative 1 there, and so there is a break, but it's not an asymptote like what we saw over at x equals 3, and not like what we saw in the example previously. What happens here? Well, let's take a look at what an asymptote is, and then we'll look at some rules. An asymptote is simply a line or a curve that our function will approach arbitrarily closely. We can get as close to this line as we want. So in this graph, what we see are the red dashed lines are vertical asymptotes. So our blue curve will get arbitrarily close to that red dashed line, or those red dashed lines. Those are vertical asymptotes. But there are other types of asymptotes. Here we have an oblique asymptote. An oblique just simply means slanted. So this red dashed curve is a line that our blue curve, our graph of our function, is approaching arbitrarily closely. So this is an oblique asymptote. Here is a horizontal asymptote. This red dashed line is our asymptote, and our blue function is approaching it arbitrarily closely. Here we have another horizontal asymptote, and you'll notice in this case our blue curve is approaching it only on the right hand side. So asymptotes can have various forms, but eventually we will approach them on one end. So with rational functions, what we will see is that rational functions have slant asymptotes or oblique asymptotes, horizontal asymptotes, and vertical asymptotes, or any combination of them. We might not have any asymptotes, but we might have some. So how do we find out what type of asymptote do we have with regard to vertical asymptotes? So if we go back to our first two warm-ups, we saw that they had the same denominator, and that denominator led to two breaks in the domain. In the first example, both breaks ended up being vertical asymptotes. In the second warm-up, though, we had a hole and a vertical asymptote. So how do you know which one's which? So first thing that we're going to do is we're always going to find the domain of the function. That will tell us any breaks in the domain. And then we factor and cancel any common factors. So if a factor cancels completely out of the denominator, then that would correspond to a hole. If the factor remains in the denominator, then that factor corresponds to a vertical asymptote. So let's take a look at an example. Here we have a function, and we're going to find its domain. So we'll take the denominator and set it equal to 0. So this would yield x equals 3, x equals 7, which we exclude both. So negative infinity to 3, union 3 to 7, union 7 to infinity. So how do we know if we have vertical asymptotes or holes? Well, what we're going to do is we're going to simplify our function. So we've already factored the denominator. It factors into x minus 3, x minus 7. If we factor the numerator, we have 2x into x. The signs will be different. So let's try plus and minus, and let's break up 15 as 5 and 3. So let's go ahead and look at this to see if it actually foils out to be what we want. So first it would be 2x squared. Outside and inside would be negative 6x and positive 5x, which yields the negative x. And then lastly we get our negative 15. So the factorization in the numerator is correct. So we'll notice that we can cancel x minus 3 and x minus 3. Now why can we do that? Because we're dividing those two. And if I divide something by itself, we get 1. But there is one instance where we do not get 1. And that's if I take 0 and divide by 0. 0 divided by 0 is not 0, and 0 divided by 0 is not 1. It's what we call indeterminate. So x minus 3 divided by x minus 3 is 1 as long as x does not equal 3. So the way we write this is we cancel those two, and then we say, okay, this is equal to 2x plus 5 over x minus 7. Now we said that was only true if x minus 3 isn't 0. So this is true if x is not 3. That's when x minus 3 would be 0 after all. So now, what linear factors do we have in our denominator still? X minus 7 is our linear factor, and so it's stayed, and therefore that is our vertical asymptote. So our vertical asymptote is x equals 7. That means that the whole corresponds to x equals 3. Now, what is the y value for that whole? So to find the y value, we're going to put it at where it would have been. So 2 times 3 plus 5 over 3 minus 7. So that would give us 11 over negative 4. So negative 11 fourths. So if we take a look at the graph, let's go ahead and graph it in Desmos. And if we again hover over and press on the curve, or depending upon if you're using the computer or if you're using the app, you can click on the curve and then follow it to x equals 3, and you should see a hole. Now also we should see x equals 7 is that vertical asymptote, which we do indeed see here.